Welcome to Fields in Spacetime. I'm Tom Giblin. Over the next 14 weeks, we're going to explore electricity, magnetism, special relativity, and how these topics intersect. As importantly, though, we're going to be learning about how science is actually done, and how the discovery of electromagnetism changed the scientific method. You may be surprised that you're first seeing me here rather than in person, but I assure you there is a good reason for this. Reading textbooks and listening to lectures are ways of ingesting knowledge, and this, it turns out, is relatively easy, and sometimes a lot of fun. On the other hand, digesting knowledge and the process of synthesizing that knowledge is hard, and I want to make sure that you've had a chance to do some of that synthesis during the limited class hours that we have. Hopefully by doing this, we'll be able to really address everyone's questions and concerns together in class before you have to sit down to work on your problem sets. As always, though, email me, come to my office hours, raise issues in class as they happen. We're all in this together, even though sometimes only electronically. So let's start with something that you're familiar with. If I wanted to come up with a model of gravity, I would do it in 3 steps. First, I would observe something. We generally call this the phenomenon. And so in this case, let's consider we have a box, and we hold it out at arm's length, and we let it go. What's going to happen to it? Well, it's going to fall. And we know that because we've dropped a lot of things, sometimes for better, sometimes for worse, but every time we drop something, it seems to fall. Once we've discovered that phenomenon, we then want to be able to describe it with a mathematical model. And you spent most of first semester physics describing how things move in a uniform gravitational field, and so you know that our mathematical model that describes this is that the magnitude of the gravitational force experienced by the box is proportional to its mass, where the constant of proportionality is g is equal to 9.8 meters per second squared. And the beautiful thing about this mathematical model is that once we've written it down, it now describes every box, not just the box that I started with. And so that's the last and important step of how science is done, that my mathematical model is more than just something that describes a single phenomenon. It leads to prediction, so that no matter what I'm dropping, no matter what box I'm looking at, it's going to experience the same mathematical model. But of course it doesn't stop there, because once I have my mathematical model, I can now start to apply it to other systems. And I keep applying it to other systems, bigger and bigger boxes, until I get to a place where the mathematical model no longer describes reality. And that's an important step, because I've now come to a stage where I have a new phenomenon. Now, it could be a rocket going into space. It could be a planet going around the sun. Either way, we know that there are situations in which the description of the gravitational force as just the mass times g is not going to work, and it requires us continuously to come up with new descriptions of gravity. And so we know, thanks to Newton, that the universal law of gravitation, which does apply to these two systems, tells me that the magnitude of the gravitational force is actually proportional to the product of the two masses divided by their distance squared. And this gravitational interaction then greatly expands the realm of validity of our previous expression. So rather than just having gravity that describes things in our room, we now have gravity that describes things in our solar system, perhaps even in our galaxy. Now there's lots of interesting physics then that tells us what happens when we start looking at galaxy scale gravity, but we'll just leave it there, that we now have a mathematical model that can start to make us new predictions. And so where do we end up with when it comes to charge? So you may have had an experience where you're, say, at a friend's birthday party, and you rub, say, a balloon on your head. So I take a balloon, and I rub it on my hair, and I find out that as I pull the balloon away, my hair is attracted to the balloon. right? So there's some force now that's acting on my hair that is not like the gravitational force. Remember, my previous prediction said that my hair should fall towards the ground proportional to its mass. Clearly, I have a new phenomenon. Well, how can I mathematically describe that phenomenon? Well, first, I need to make a full set of observations about what's going on. And I'm going to describe just two of them. And I think these are two that you've had in your general experience. But the first is, I take the balloon, I rub it on my hair, and the balloon and my hair are attracted to each other. But if I take that same object, that balloon that I've rubbed on my head, and I now bring it, say, close to another object that I've rubbed on my head, say some streamers or something, then I'll find that the balloon and the streamers actually repel each other. And so I see in my phenomena that I both have a force that can sometimes be attractive and a force that can sometimes be repulsive. So let's make some definitions. In order to describe a phenomena such as this, where I have both attractive and repulsive forces, I need to come up with a more sophisticated mathematical model. To do that, let's start with some definitions. First, the inherent property that we're going to be dealing with is something that we call charge. And like mass, charge is going to be an inherent property of the material that I'm looking at. For example, I can assign a certain amount of charge to the balloon. I can assign a certain amount of charge to my hair. And those two things are going to go into the mathematical model that I'm using. We generally denote charge with little q, and we measure it in the unit of coulombs, which we denote with a capital C. Now, in order to have a repulsive and attractive forces, I actually need now two kinds of charges. And I think you can think about this in terms of your experience with positive and negative numbers. In order to come up with an answer that has two different signs, that is, in order to come up with an answer that can be both attractive and repulsive, I'm going to need two different kinds of input. The logic table generally goes plus times plus gives me a positive number, minus times minus gives me a positive number, but minus times plus gives me a negative number. So in order to have two different results, I need to have two different inputs. At a more basic level, those two different types of charges, plus and minus, come from two different types of subatomic particles. Now, you've learned about these in your maybe chemistry or physics classroom, but what differentiates the proton from the electron is the sign of its charge. So we're going to take the proton to be the fundamental positive charge, which has a charge of E, and the electron to be the fundamental negative charge, which has a charge of minus E. Now, it turns out that I've told you that charge was measured in coulombs, but here I've given you the charge of the proton and the electron in terms of E. Well, 1 coulomb is a ton, maybe not literally, but is a lot of E's. In fact, there are 6 times 10 to the 18 E's per coulomb. So that's a lot of protons or electrons. And when I put all of this together, I can now write down a mathematical expression that helps to reflect what I've seen in my phenomena. And that is that the magnitude of the force is proportional to the product of the two charges divided by the distance between them. And this relationship here is what's known as Coulomb's law. And you'll find that you're pretty comfortable with this because it looks a lot like Newton's universal law of gravitation. That is, the strength depends on the size of the two charges involved, and it decays as 1 over r squared, which is why the balloon at your friend's birthday party is more attractive to your hair than it is to your friend's hair. The constant of proportionality here is very different, though, than what we saw in Newton's law. In Newton's law, big G was a very, very small number. But when I try to express electromagnetism in terms of meters and newtons, I end up with a constant of proportionality, K, which we also sometimes write as 1 over 4 pi epsilon naught, and that's for historical reasons, and we will talk about that later in the semester. But that number itself is very, very big. And so when I write down Coulomb's law in general, and I always spell this word wrong, I get that the magnitude of this force is equal to K times the magnitude of Q1 times the magnitude of Q2 divided by r squared. And you'll notice I'm being pretty careful right now by writing all of my charges and forces in terms of their magnitude. And that's because for the time being, I have to keep track of all of the directions sometimes we call them signs. I have to keep track of all of the directions myself. So I know that the magnitude of the force is going to be given by the expression in Coulomb's law, but the direction of the force, whether it's attractive or repulsive, is something that I often have to take care of on my free body diagram. It's possible, and we will mathematically quantize this next time, but for the time being I want us to focus on the fact that the strength of the interaction here is given by the product of the two charges divided by r squared. And the last thing I want to note, and this is just a teaser for your future classes in physics, that charge is conserved. Much like mass, although perhaps even more fundamentally than mass, we know that charge can never be created or destroyed, but it can flow. And we already saw that it can flow because when we rubbed our head against the balloon, we saw that charge was redeposited between the two so that there was an excess of one type of charge on one object and an excess of another type of charge on the other object, which allowed them to attract each other. Next time, we're going to go a little bit deeper into Coulomb's law. We're going to study it in terms of free body diagrams and also be mathematically precise about all of the signs and directions involved.